Welcome to this video on ordinary differential equations. This is actually the first video in a series of 4 videos, so if you're already quite familiar with ordinary differential equations, feel free to skip forwards to the next videos which will explain specific solution techniques when it comes to ODEs. But in this video, we'll just look at the general concept of an ODE, the most simple technique of all, which is direct integration to solve it, and then also looking at equilibrium solutions and slope fields. So that's what we'll cover in this video. Okay, so what is an ODE? An ODE is an equation with an unknown function that has one independent variable. The ordinary part is it having one independent variable. The differential equation part is that the unknown function is given to you in terms of its derivative. And unlike previous equations that we're used to dealing with in maths, where the unknown variable is a number, a constant, x or y, what we're trying to figure out now is what a function is. So at an abstract level, we're solving the equation for a function as the solution, as opposed to a number or a variable x and y as the solution. So some examples of ODEs are given here below. dp on dt is equal to k times p, where k is some constant, and this means that the derivative of p is equal to itself multiplied by k, and this is in terms of time as the variable. This has order 1 as an ODE because its derivative dp on dt is the highest order derivative in this equation, and the order in ODE is just the highest order derivative in the equation. So in this one below, we've got mx dot dot is equal to minus kx, so the order is equal to 2. And in this case, m and k are constants, and x, when it's got the dot above the variable here, usually means it's in terms of time, and it's the derivative twice with 2 dots there. Here we've got y prime equal to xy. This has order 1 because you have y prime as your highest order derivative. And then this example here, we have x y prime prime squared plus y prime 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 plus 4y to the 5 equal to y prime. That's quite a hectic ODE, but the order of this ODE is 3. We don't look at the power here 5, we look at the highest order derivative, which is this one here, which is 3. So that's what ODEs look like, and there can be many different types of writing it. You got the dot method, the dash method, the straight up dp on dt method. Any of those are pretty common, and they usually mean the same thing but just written in a different way. So for our solution techniques, there are many different types of solution techniques, and usually what you want to do is be well versed in the ODE literature and understand several different types of techniques, and then when you are given a ODE, you identify the type of the ODE and then the correct tool that is appropriate to dealing with that type, and then solve it. And so in this series of 4 videos, I'll take you through different types of ODEs and different tools to solve it. And those are great for when you're starting out with looking at ODEs. And the very first one is the most simple of them all, which is just direct integration. So if you're given dy and dx is equal to f of x here, then simply find your unknown function y by integrating both sides with respect to x, and integration is the antiderivative, so that will, I suppose, undo differentiating with respect to x and just give you back your y. That's what's represented here. And then whatever your integral is on the right hand side of this function f of x, that will then give you the solution to this ODE where y of x is equal to whatever that integral is. And of course this is very simple and is more considered integration than an ODE, but I suppose there's a good place to start when it comes to ODEs. Of course you cannot always do this method. I mean, simply looking above at something like this one here, or even this one here, once you start to integrate that with respect to x, you're going to get a problem because you have other things that get in the way of your standard integration techniques. And that's why we learn other methods to solve ODEs. Okay, so something that is important to know when it comes to ODEs as well is that the solution is not unique, especially because if you're unknown function is given to you, if the equation is given to you in terms of the derivative of the unknown function, there might be several functions that have that same derivative, and any one of them is a valid solution, a valid answer to this equation with an unknown function. And the most obvious example of this is given here, where you have an unknown function y where the derivative is equal to 2, and that will just be any straight line that has slope of 2 and a y-intercept of plus c, which is some real number. Any of these lines will give you this derivative. And so if you are not sure what the function is here, you need more information to work out specifically what this c is. And in ODEs, we call those initial value problems, where you're given an extra piece of information, like this is the slope of the line, and the line passes through the point, the point 1, 2, and that would suggest that the plus c is actually just a plus 0. Okay, so the next thing I want to look at in this introductory video on ODEs are equilibrium solutions. Equilibrium solutions are important concept when it comes to ODEs, because sometimes when we're given an unknown function, we're not really caring about exactly what the equation is for that unknown function as much as we're caring about the equilibrium or equilibria that fall out of that unknown function. And an equilibria represents some sort of steady state, some fixed point where the state of the system is held constant, as in it is in balance. And an equilibrium solution is constituted by this variable just being the same as time progresses. So we're looking for some sort of answer where the derivative is equal to 0, and over time y is not changing at all. So an example of this would be if y prime of t is equal to minus 3 multiplied by y minus 1, when is this equal to 0? Well, it's equal to 0 when y is equal to 1. So when y is equal to 1, the derivative is going to be 0, and so the function y will remain constant. And if it's already equal to 1, it will remain at 1. And then as time passes, it will stay at 1, and the derivative will stay at 0, and it will just be in equilibrium and remain at 1 indefinitely. And what is interesting in analysis of the dynamics of this system is understanding how will the ODE progress. Will it progress towards the equilibrium, away from the equilibrium? What is going on? So to understand the answer to that question, we look at what the derivative is when y is greater than 1. And in this case, when y is greater than 1, we know that this here is going to be a positive number, and then minus 3 here multiplied by a positive number will give us a negative number. And so the derivative will be negative, and that will be pushing y towards 1 if it is currently above 1. If y is less than 1, then the derivative is going to be positive, because you have a negative number in this bracket here, a negative number outside this bracket multiplied together is a positive, and so y will be increasing if its starting value is less than 1. And what that looks like in this diagram here is that the slope, which is the derivative evaluated at this level of y, will always be negative, heading towards our equilibrium of 1 if it is starting off larger than 1. And then if the y value is less than 1, it'll be positive, heading towards the equilibrium as well, increasing in value towards y is equal to 1. And so over time, no matter where you start, whether you start at 1, above 1, or below 1, you're always going to be heading towards 1. And once you reach it, you will remain in that equilibrium point indefinitely. So this is what we call a stable equilibrium, one where the system over time will progress towards this value, and once it reaches this equilibrium value, it will remain there. And just to wrap up this video, this is the beginning of analysis of the dynamics of y, studying how it changes with respect to y, to time given its starting location. And that's something that we find very interesting in terms of ODEs, is understanding the dynamics of the system and how it will change over time. All right, this is just the introductory video for ODEs. In the next videos, we'll look at first order linear ODEs, second order linear ODEs, systems of ODEs, separable ODEs, and how we want to solve those together. All right, thanks for watching.